Good afternoon, everyone. There will be two talks today. The speakers will be available at the foyer from 6 to 6:30 p.m. for those of you who are interested. And Professor Prerana Chatterjee and Professor Rakhi Singh will hold office hours from 6:30 to 7:30 p.m. in the main hall. For the first talk of the day, we have Dr. Riddhipratim Basu with us. He is an associate professor at ICTS. He is majorly interested in probability theory and its applications. His recent works include first and last passage percolation, interacting particle systems, and large deviations. Today, the topic of his talk is going to be structures in randomness and invitation to probability theory. Please welcome Dr. Riddhipratim Basu.
Thank you. Am I audible? All right, great. Yeah, thanks for the invitation. I would like to start by thanking the organizers for the invitation and for the introduction. So it's a great pleasure to be speaking here. So as was mentioned, I'm a probabilist by profession, and as my title says, I'm going to invite you today to learn probability theory. I'm trying to explain why it is interesting and fun to learn probability theory and also useful. And I know that you guys have had a long day, hard working day. So I'm going to be not very technical. So we'll just start with talking a little bit about what is probability, which most of you, I am assuming, know. I mean, you have seen some amount of probability in high school and undergrad. So what we are trying to do in probability theory is basically trying to model and study uncertainty. I mean, the world around us is full of uncertainty. So it's an important thing to be able to model and study uncertainty in various contexts. And the basic principles underlying the probability theory goes back millennia. Most often tied to the study of gambling. Human beings have an irresistible attraction to gambling. In the context of gambling, the study of some principles underlying probability goes back thousands of years, although the systematic study of probability theory actually does not start until much later. It's much more recent than many other branches of mathematics like geometry or number theory. So systematic study of probability starts somewhere in 16th or 17th century. I'll say a little bit about it at the end where I talk about historical context. But although it's rather young as a branch of mathematics, it has turned out to be extremely important. And it's important in all branch of empirical sciences and quantitative sciences like statistics, physics, biology, computer science, you name it. In all of these branches, probability theory has found important applications. And additionally, it has also emerged as a core area of pure mathematics. This has happened over the last 50 years, largely. And this is due to the fact that people have discovered many interesting and non-trivial connections to many other different branches of mathematics, such as partial differential equations, functional analysis, complex analysis, combinatorics, dynamical systems, and so on. Okay, so here is the plan for the talk. So the talk is roughly split up into three parts. So I'll talk about two fundamental results. So this will be the most technical part of the talk, which is not very technical. And then I'll tell you about some of the important questions of recent interest, what people doing research in probability theory like myself think about. And then at the end, I'm going to talk about a little bit of history. I call it probability through the ages. People who had major contributions in developing the theory of probability and who are the major players in this field today. I'll talk a little bit about that. So that's the plan for the talk. Okay. So let's start with two fundamental results. Let's try to motivate these results and why, how they kind of naturally come up. I'm sure if you have seen any probability theory at all, you must have seen coin tossing experiment. You toss a fair coin. Well, fair means what? So it has equal chance of coming up heads or tails. So that's what a fair coin means. And you toss it in an independent way so that if the first coin toss turns head, it doesn't affect the second coin toss. So suppose you have a sequence of independent fair coin tosses like that. And this is kind of a very basic growth model. So what you do is that you're creating a pile of boxes. Okay, so every time you see a head, you add a box. So at time n, there will be some number of boxes piled up, but that number is not fixed. It depends on how many heads you have had. So it's a random variable. And one kind of interesting question to answer for various reasons is to understand at some large time n, what is approximately the height of this pile. See, this is goes back to the title of my talk. So a priori things are random, but what the objective of probability theory is to find patterns and structures in such randomness. So of course, the number of boxes in the pile, the height of the pile is going to be random. It's not going to be fixed. But as n becomes large, you're still going to see some structure. And what is that structure? So let's try to formulate first in sort of a mathematical way. You must have seen this kind of things. Many of you have, I'm sure. So how do we sort of mathematically translate this question? So let's look at the random variable xi, which is 1 if the ith toss turned up a head and 0 otherwise. So these are called Bernoulli random variables. Probably all of you have seen that. So these are Bernoulli half. Half is because the chance of head and chance of tails is a half-half. So probability that it is equal to 1 is half. So that's a Bernoulli half random variable. And the height of the pile at time n is exactly sum over I from 1 to n xi. Because every time there was a head, I added one box to the pile. So this is exactly the height of the pile at time n. Now, what we are asking is, what should Sn look like as n becomes large? Now, how does it grow? So, of course, Sn is increasing. As n increases, Sn increases. So how does Sn increase? Okay, I mean this, I'm sure at least intuitively you all know the answer. So what should the large time behavior of Sn be like? N by 2. So what can you make it a bit more precise? Because it's not going to be a fixed number. So what n by 2 is going to be? So every time, so the idea is that every time there's a chance half that you increase by 1. So roughly, or if you want to be more precise, on an average, you're going to see n by 2 heads. So if you are familiar with the notion of expectation, this tells you that expectation of Sn, the average value of Sn, when you average over the randomness, is going to be n by 2. Actually, something stronger is also true. What is true is that if you make n larger and larger, and you look at the fraction, instead of looking at Sn, if you look at Sn by n, which has average half, by the way. So we just said average value of Sn is n by 2, which means average value of Sn by n, the fraction, is half. But not only is the average value half, the statement is that as n becomes larger, so in the limit as n goes to infinity, this value, this fraction Sn over n, will actually converge to half. Now, these are not real numbers, so the notions of convergence is slightly different and slightly technical, but I won't go into that. But you should think about it in the following way. So what does it mean that Sn by n goes to half? It means that if you take any fixed level of error, let's say your error is 0.01. So then what it says is that if you look at the chance that Sn by n minus a half is bigger than 0.01, so Sn by n is either smaller than 0.49 or bigger than 0.51, as n becomes large, that chance goes to 0. So as n becomes large, that chance becomes smaller and smaller. Okay, that intuitively at least clear. So that's what it means to say Sn by n goes to half. And this is an example of the so-called law of large numbers. Any questions? By the way, if you have any questions at any point, feel free to stop me. Yeah. So error in the difference. So Sn by n minus a half. So let's say I fix my error as 0.01. So then I look at the chance of an error bigger than 0.01 happening, which means that Sn by n is either less than 0.49 or bigger than 0.51. So that means that this error, Sn by n minus a half, that is bigger than 0.01. So the chance of that error happening, so this fixed error 0.01, that happening that chance will go to 0 as I make n large, n large. And this will be true for every fixed error. So if it will be true also for error 0.001, 0.001, 000, 10 zeros 1, everything. Okay, so that's what it means to say that Sn by n goes to half. So this is, if you want to be technical, this is what is known as the notion of convergence in probability. So in a probability textbook, this statement will be phrased as Sn by n converges to half in probability. There's a slightly stronger notion which is called almost sure convergence, but not important for our purposes. But this phenomenon, is it really important that we started with this sequence of biased coins, unbiased coins? What happens if the coin is biased? So instead of probability half of turning up a head, what if it was 0.6? What should the result be in that case? Yes? Okay, so you're saying that this limit should then be 0.6 rather than half. Okay, yeah, that's a reasonable guess and correct also. What if we do something more general? So suppose instead of tossing a coin, we roll a die. And instead of adding either 1 or 0 boxes at a time, we add the number of boxes equal to the face that shows up in the die. What will happen then? Is there some kind of a pattern here? So suppose we roll a die 1 to 6 and suppose it's really random, so all the faces turn up with equal probability. What is the chance that so what do you think? So now my Sn will be again summation xi, but xi's are no longer 0 or 1. They take these values 1, 2, 3, 4, 5, 6 with equal probability. So can we say something similar in that case also? Okay, that's great. So how do you get this 3.5? Yeah, so 3.5 is the average of what you get by rolling a single die. So that's what again the correct answer is. So what is the general principle here? So the general principle here is what is called the law of large numbers. So the result says that, so you have any sequence of, so IID means independent and identically distributed, if you haven't seen that before. So if you have any experiment that you repeat independently a large number of times, and xi is the outcome of that independent, so it's some real number or real valued random variable if you want to be precise, then you define Sn exactly in the same way. So Sn is the partial sum, Sn equal to x1 plus x2 up to xn. And the average, so what we assume about these xi's is that they have a finite average, like half, 0.6, 3.5. So all these experiments that we described, the outcomes have a finite average. I mean, there are examples where I can have infinite average for the outcome. We're not bothered about those. So let's just consider experiments where the outcomes have finite average. And in that case, this general principle holds. If you look at the partial sum, divide by n, as n goes to infinity, they converge, again in the same sense that we described before, to the average of the single experiment, which is a mu. So this is called the law of large number. It goes back at least to early 17th century by Jacob Bernoulli, after whom Bernoulli random variables are named. And then the more general versions were proved in the early 20th century by Khinchin and Kolmogorov. Again, these are major figures in the development of probability theory. I'll come back to them later. But let me give you another example. It's better to just show you a picture first. Okay. Okay, so what are we doing here? So what we're doing here is we're taking the unit square. Maybe just. So so this big square is like the unit square, and the circle is the circle inscribed. So it's okay. So let's say it's not the unit square, it's the square from -1 to 1. So the square of size 2, and the circle inscribed is the unit circle, x square plus y square equal to 1. Okay. So what are we doing here? What is this experiment doing? By the way, this is it's not mine. It's somewhere in the internet. The link is there in the talk, you can find it. So what we are doing is that we're dropping points uniformly in the square, and the points that are inside the circle, we mark them red, others we mark them blue. So what we are doing is that as we drop a large number of points, we are calculating fraction of red points. Now, can you tell me, by using the previous law of large numbers, what should the limit be for this fraction of red points? Yes. So what is the chance that when I drop a single point uniformly in the square, I'm sure you know what that means. What is the chance that it lands inside the circle? Okay, yeah, so speak up. Exactly, so area of the circle. So because it's uniform, so probability of your point landing in any region is proportional to the area of the region. So the probability that one particular point is red, that is area of the circle divided by area of the square. What is that? Pi over 4. So now law of large number tells us that as n goes to infinity, this fraction that I get from my experiment will converge to pi over 4. So if I multiply that by 4 and take n very large, I should get a very good estimate of pi. And this is what you see. So this is the estimate of pi that they're getting. No, we all know value of pi is like 3.1415. So it's not very far off. 3.137. Okay. So this is the example of a very important method in many applied sciences. This is called a Monte Carlo method. So Monte Carlo method uses this kind of probabilistic experiments to estimate something. So this gives you a way to estimate the value of pi by performing some random experiments. And then there are more sophisticated versions of Monte Carlo estimates like Markov chain Monte Carlo, which I don't know if you're going to see that, but that's another sort of very useful tool in many applied sciences. Okay, so what I just said is basically written here, so I'm not going to get into that much, but I should tell you that I don't know if any of you have ever seen the Buffons Needle problem. This is a version of this, the same thing, which does not require you to sort of drop points uniformly. Have any one of you seen this problem before? Buffons Needle problem? Have anyone of you seen this? It's a very famous problem. Okay, so let me not get into that, but this is sort of another experiment that gives you a way to estimate pi, which was historically done earlier, like early 1800s and so on. You know, when people did not know how to generate a uniform random number. Okay, so this is, let me not get into that. I mean, if I have time later on, maybe I'll get into that. But now let us ask this question, like, how good these are in practice. So I told you some result which says that as n goes to infinity, something happens. But in practice, n will never go to infinity. You can never repeat an experiment infinite number of times. You will have to stop at some large n. So it is important also to understand how large n would need to be for your approximation to be good enough. So, what would you typically expect? So here are some, again, important historically famous examples. So Buffon, the same as Buffons Needle problem, he did an experiment again in like late 18th, early 19th century, where he tossed a coin 5,000 times and he got 2,048 heads. John Kerridge, who's a South African mathematician, he was house arrested in Nazi-occupied Denmark during the Second World War. So he had nothing else to do. So he spent his time doing lots of these experiments. So he tossed a coin 10,000 times, and he got 5,067. And Carl Pearson, a British statistician, I absolutely have no idea why he did that, why he had so much time to do 24,000 tosses. He was not arrested or anywhere else as far as I know, but he did it 24,000 times and he got 12,012 heads. These are pretty close to half. But now the next question you should ask, how close is close? No. Are these close enough? Are these good enough to sort of you to believe the law of large numbers? Okay, so that's the next question. So these are kind of questions you ask in statistics. These are called statistical inference. So let's kind of do a baby statistical inference question. So suppose I do this coin tossing experiment, I toss a coin 100 times and we get 60 heads. Now, suppose I tell you that, okay, this is a fair coin. We got 60 heads, so it's a bit larger than 50, but you know, it's random, so it's still a fair coin. Should you believe me? So how should you check? So this kind of questions, these are called testing of hypothesis in statistics. So how should you go about, whether you should accept my hypothesis that it is a fair coin or reject it and say that no, this is not a fair coin, 60 is too much. So the right question, or one of the way to approach this question, is to look at the following quantity. So I look at the chance that suppose my coin was actually fair, then what is the chance that I would get 60 or more heads? So if that is large, then you tend to accept my hypothesis. But if that is so very small, then you should not accept my hypothesis, because then the chance of you being right despite what you have observed, the chance of I being right despite what you have observed should be very small. And in that case, you can actually do the calculation. I mean, this is, you can write down a formula and do the calculation, and it turns out to be like something like 0.03. Okay, and is it small enough? That you have to decide depending on how much error you can afford. But this is the quantity you should look at. This is something known as type 1 error in the statistical inference literature. But again, we would like to have a more general theory. So what if I had 55 heads? Should I do this calculation again with 60 replaced by 55? What if I did not have this coin tossing experiment, but I have this die throwing experiment? What do we do then? Again, can we find some general principle? So this is sort of, again, a demonstration I wanted to show you. This is called the Gton Board. I don't know if you have ever seen this. Siva has one in his office. Yes. So what we are doing here, so let's just do this. Okay. So what we are doing here is, that we are dropping a ball, say, from the top of this triangle, and then at every step it goes down, it sort of chooses either to go to left or to go to right. And it does that sort of uniformly. So it chooses with chance half to go to right, chance half to go to left. And then we collect it at the bottom. Now you can see that this is basically the same as this coin tossing experiment that we had. So there we added +1 or 0. Here what we're doing, we're adding +1 or -1. So we're either going left or going right. So it's basically up to some linear transformation. This is the same as this coin tossing problem. And we're doing this experiment multiple times. Many times. So every time a ball is dropped, you look at what is its location at the bottom, and you add height 1 to this histogram that is there. And for large n, this kind of gives you an approximation of what is the distribution of this quantity Sn. What is the, so are all of you familiar with the histograms and similar things? Okay, so basically, histograms are supposed to approximate the distribution of a random variable. If you get observations from a distribution and you get a large number of observations and plot a histogram, then that should approximate the distribution. And what is happening here is that you can see that there is roughly this bell-shaped curve that is happening. Actually, I want to show you an actual experiment how it works. So let's see, it should be here from Wikipedia. Let's see the video. Yeah. So yeah. So this is what a Gton board looks like. So these balls are dropping, and they're hitting these pegs, and they're moving either left or right. The pegs are like placed so that the deviation is symmetric, and at the end you get this histogram. And again, you see that you get this same shape like a bell curve. Okay, so this is what Francis Galton invented in the 19th century to visualize these distribution of Sn. Okay. So now, so what this kind of suggests is that as n becomes large, there should be some limiting shape that this distribution should have. Okay, so if you look at this histogram, they look like they're converging, they are converging to some nice shape. And one can actually show that this is indeed the case. So as we have seen before, so average is n by 2 of this quantity Sn, and variance, I'm assuming that you are all familiar with the notion of variance, which is the square of the standard deviation. So variance is n over 4. It's easy to calculate because it's sum of independent random variables. So variance of sum is the sum of variance. And one can show that the probability that this quantity Sn, if I subtract of its mean and divide by the standard deviation, which is square root of the variance, probability that it is bigger than x as n goes to infinity, that converges to this nice function. And if you have seen normal distribution before, you can see this is just the probability that normal distribution is bigger than or equal to x. So what this statement means is that appropriately centered and scaled, this quantity Sn actually converges to a Gaussian distribution, a normal distribution. And this phenomenon again is very general, so which brings us to the second theorem, which is the most famous theorem in probability, called the central limit theorem, which says that if you have a sequence of, again, so the basic setup is the same as before. So we have a sequence of independent and identically distributed random variable with mean mu. Now we have an additional hypothesis which says that the standard deviation is positive and finite. Sigma square is a variance, sigma is a standard deviation, which is positive. We assume it to be positive and finite. Then the quantity Sn, so this is just the Sn minus n times mu divided by sigma times square root n, which is, again, it's just to rephrase, this is Sn, this is mean of Sn, this is variance of Sn, or standard deviation of Sn. So you take Sn, subtract its mean, divide by the standard deviation, and as n goes to infinity, it becomes close to a normal distribution with mean 0 and variance 1. So this is what is called the weak convergence. I'm not going to go into the definition of that, but again, I mean, you can take it as this to be the definition of this convergence. So probability for every x this converges, probability that the scaled quantity is bigger than x converges to probability a normal distribution is bigger than x. So for Bernoulli distribution, this was proved by de Moivre in 18th century. The more general statement comes from Laplace in 1805, and the more general, so the ones that you see in textbooks these days are largely due to people like Lyapunov, Lindeberg, and Feller. I did not have enough space to put all their pictures, but these are, it goes back to like 1730s, but the most general versions are more recent. So how this sort of connects to the problem that we started with? So this tells you that this quantity, we can sort of calculate the probability that this is bigger than or equal to x by just calculating the corresponding probability of the normal distribution. So of course there is an error, again, because it's again an approximation as n goes to infinity, but then there will also be ways to bound that error. So let's not worry too much about it. In practice, this approximation works very well, even with not a very large number of samples. So basically, whenever you have observations from independent identical observations from a population with finite mean and variance, you can basically do this testing procedure. So if I tell you that the mean is mu, and you observe that the average of your observations is much larger than mu, you can do a test. So you can calculate what is the probability that if the actual value was mu, what is the probability that I get an observation which is much larger or much smaller. And that calculation I can do for the Gaussian. So I don't have to do the calculation for every different hypothesis, for every different population separately. So this is a phenomenon. It's a very important phenomenon in probability theory. It's called the universality, which is a very important topic. So what does universality mean? Universality is best to explain with the example. So this quantities mu and sigma, they are specific to the distribution I chose. They are specific to the experiment I am performing. But the fact that I subtract n times mu here and square root n times sigma here, so this n and square root n, they do not depend on the experiment. And the limiting distribution, the Gaussian, that also does not depend on the experiment. So these are universal. As long as the experiment I am performing gives you an outcome which has finite mean and finite variance, this limiting distribution is always going to be Gaussian, as long as these are independent samples from this population. And actually, central limit theorem holds in far more generality. You don't need always exactly identical, or some kind of weak dependence also works. And in some sense, this explains, central limit theorem explains why Gaussian distribution is so ubiquitous in nature. I mean, in every kind of statistic, you can see, like if you look at the height of some population, if you draw a histogram, you'll see that it looks like a Gaussian distribution. So in some sense, central limit theorem explains why these Gaussian statistics are so universal. Okay, so this is the sort of the end of my first part of my talk. So the second part of my talk, so these are so this topic of law of large numbers and central limit theorem, they are foundational results in probability theory, but they are also very well studied. So in the second part, I want to tell you some of questions which are of recent interest, what probability researchers are working on now. And they are also, you'll see that they are also related to the problems. In some way, they are problems that we had looked at. So this first question I want to tell you about is the question of random walks. So this coin tossing experiment, you can think about, it's the way, or this Gton Board experiment. So you are going to the right with probability half, going to the left with probability half, right? So you can think about, you are on a line and you are doing a random walk. So you move either to the left or to the right. So that problem is sort of a one-dimensional random walk, which is also, it's kind of a classical thing that people analyze. But you can also ask similar things in higher dimensions. So if you say look at 2 dimensions, and then you look at north, south, east, west, and you choose a step with probability 1/4 each. So that would be a 2-dimensional random walk. You can do the same in 3 dimension, any high dimension. So this is and you can do it also on more general graphs. So you don't have to do it always on like Z or Z2 or Z3. You can do it on more general graphs. So these are called random walks. So they are very interesting processes that people study a lot. So the pictures here, so the first one is the 2-dimensional random walk, 100,000 steps. And this one is a 3-dimensional. I'm not sure if you see this like dotted lines of the cube. So this is actually meant to be the trajectory of a 3-dimensional random walk after 100,000 steps. And you can already see some kind of a difference. So the 2-dimensional random walk the 3-dimensional random walk is somewhat more sparse. It's also understandable, right? Because at every step you have 6 places to go to, whereas in 2-dimensional you only have 4 places to go to. So one interesting result here is that in 2 dimension or in 1 dimension, if you start a random walk like that, it will always come back to the origin. But in 3 and higher dimensions, there's a positive chance that will never come back to the origin. So this is kind of the quote by mathematician Kakutani, where he said that what this implies is that a drunk man will always find his way home because he's walking in a plane, but a drunk bird who's flying, presumably in 3 dimensions, may get lost forever because there's a positive chance. So the idea is that if you are drunk, when you are drunk, you are kind of making random steps. You don't know where you want to go. And if you are in 3 dimensions, like a bird flying, there's a positive chance that you will get lost forever. You will never find your way home. So this is a phenomenon that is called transience, whereas the recurrence is a phenomenon which that you always come back to where you started with probability 1. So this is one topic of current interest, on more general spaces and more general random walks. You don't always have to choose like half or 1/4. You can have more general random walks with more general steps. Maybe you can move 2 steps to the right or 3 steps to the left. That kind of things are also allowed. All right, so that's the first thing I wanted to tell you. The second thing is very similar to the first growth experiment that I described. So previously we had this one pile of boxes and we kind of randomly added on top of it, right? But you can have a different experiment. So instead of one pile of boxes, you have a connected piles of boxes. And then, so it's like this. And then randomly, whenever you have these corners, you can add one box there in the corner. So I don't know if any of you have ever seen this game of Tetris. Okay, so this is exactly like Tetris, where you sort of have these tetrominos falling, and then it's a sticky version. So whenever you sort of hit a corner of the already existing interface, then you get stuck there. So these are modeling what are called randomly growing interfaces. Is are very important in statistical physics. Again, I'll show you some nice pictures. So how it actually looks like. So these are these tetrominos falling, and you can see, so the top envelope, that doesn't look quite Gaussian anymore. I mean, okay, maybe it's not clear from here, but what happens is that when you have this dependence, so this model that I described, the different columns have dependence on one another. So I cannot sort of increase one too much without increasing the other. So they are introducing a dependence among the columns, and that sort of that forces the behavior to be not Gaussian anymore. So you don't have central limit theorem for that. So what kind of behavior you have for here, it's again a topic of very important research. So there are some predictions coming from physics, which is largely unverified in the mathematics literature, probability literature so far. But this is one other kind of interesting topic of current research, the random interfaces. Okay, so let's show you some other pictures. Okay, so one other very interesting topic, it's called percolation. So what does percolation do? It studies random connectivity structures. So what is this? Let me try and explain you this picture. So as you can see, there are these parameters P. So what I'm doing is that I'm taking a two-dimensional lattice, and you can see sort of these small black lines. So what I have done is that I have not done. I have taken it from some simulation that someone else has done. But what the experiment does is that, so I have these edges in the lattice. So I have this two-dimensional box and I have these edges, right? So what I do is that I keep an edge with probability P and delete the edge with probability 1 minus P. And I do that independently for all of the edges. And what are these sort of different colored clusters? So once I remove some of the edges, the graph becomes also disconnected, right? So the graph does not remain connected anymore necessarily. So there will be some small clusters. So these different colored components are connected components of this graph where I have deleted some of the edges. So what are we trying to do? So the motivation, you can think of it as the following. So suppose I have a block of soil or something like that, and then some parts of the soil are hard where water cannot pass through, and some parts of the soil are porous where water can pass through. And the question I want to ask is that if I put some water at the top of the surface, will it percolate to the bottom? So that is the kind of questions that we are trying to answer here. So how are we modeling this? So these places where the edge stays are the porous parts, and the places where the edges are deleted, they are the impermissible parts. So this inhomogeneity in the medium, they're all often random, or not easy to model in a deterministic way. So they're often modeled as random. So what this shows is that there is no sort of large connected cluster in the left. That means that the water cannot go too far. So if you put some water somewhere, it cannot go too far. It will get stuck within the small cluster of its own. Whereas if P is large, that means the porosity is large. Then there is this one big green cluster. That means that if you put a water somewhere, some water somewhere in that green cluster, it will percolate eventually everywhere in the space. So this is a general phenomenon in percolation called phase transition. So in the phase in the left, this is called subcritical, which means that you do not go very far. Whereas in the phase in the right, it's called supercritical, which means that you are sort of connected to infinity in an idealized sense. So let me show you how stark it is. So let's go to this simulation. Okay. So I can choose a probability. So let's choose 0.49. Okay. So it's kind of clear that larger P is, the larger these clusters are going to be. So this is 0.49. This is already, you can see that clusters are kind of big, but not very big. But now I'll go to 0.51. Now you already see there is a one large cluster connecting everything. There are some small islands which are not connected, but this large cluster that connects everything. Okay. So this behavior goes a rapid change as soon as I change from P from 0.49 to 0.51. And this is one of the most famous theorems in sort of 20th century probability, which shows that the transition happens exactly at 0.5. So if P is less than 0.5, then you have the small clusters, whereas if P is bigger than 0.5, then you have one giant cluster. This is a phenomenon of phase transition. So this is it's one of the most famous theorems of like last 60 years of probability theory to show that the transition happens exactly at half. Okay. Now I'm just trying to give you flavors of different kinds of questions that people look at. So this was one. Let's see what was there. Okay. So the next thing I wanted to show you is, I don't know, you probably will see a bit of random matrices maybe in this summer school. So one other thing people study is that instead of random variables, like real valued random variables, people also often study random matrices, where you have a matrix full of random entries. And then the question of interest often is to study the eigenvalues. So this is a plot of eigenvalues of a large n by n matrix with IID, independent and identically distributed entries. And you scale it properly, and it turns out that the eigenvalues are kind of uniformly distributed on a circle. This is called the circular law. So there are many, this is one of the famous results of probability theory in the last 30, 40 years. And people study a lot of other spectral properties of random matrices. You know, what happens if you had a little bit of dependence? What about the eigenvectors? So random matrix is another very active area of probability research. The final thing is about random networks. So this is a picture taken again from Wikipedia, like all my pictures. So this is basically the network of the internet. This is quite old. This is like from 2005. So what the nodes are like IP addresses, and you connect them if one IP address links to the other. And this is like 30% of what internet was in 20 years ago, 2005. And the length of the edges sort of is proportional to the lag time between in that connection, something like that. I'm not too sure. But okay, so this is just a nice picture. So the point is that there are many kind of real life situations where you have such huge networks, where the connections are somewhat random, you know, like Facebook, or some social media where the nodes of the network are people and the connections is like friendship network. So you are connected to people you are friends with. So understanding these networks are particularly important in many areas of science. And so to study random networks, so what do networks look like? So what kind of random networks will model a picture like this correctly? So that answering that kind of question, it is very important. And network theory again is a very important topic of recent research. So yeah, so these are sort of 5 representative topics of current probability research. And again, don't think for a moment that these are all. This is sort of what I have chosen from my personal bias, but there are many other interesting problems. I mostly chose these because they had nice pictures, and this because I like them. But these are some of the interesting topics of probability research, which brings the second part of my talk to the end. How much time do I have? So, okay, I see. Sure. So, okay, the final part of my talk is a little bit of history of probability and probabilists through the ages. Yeah. So actually, so this picture, I mean, this story starts from 16th century, but as I said, so the basic principles of probability theory kind of go back at least 2000 years, if not more. So it's a curious thing I recently found out that that in Mahabharata, there is a story where they say that to count the number of leaves in a tree, you don't have to count all the leaves. You basically take a branch, you count the number of leaves in a branch, and you can estimate the total number of leaves in a tree by multiplying that by the number of branches. So it's basically something like sampling theory. So they call it the theory of dice, apparently. So of course, and you all know that there's this gambling games in Mahabharata. They talk about fair games and things like that. So some principles of probability theory did exist. Understanding did exist at that time, and also in other parts, like Greeks also had some gambling games and some theories of that. But the systematic study, it kind of starts with this guy, Cardano, who's an Italian mathematician and an avid gambler. So basically, Wikipedia says that, so, okay, he's quite famous. So he's the first Western mathematician to use negative numbers in a systematic way. But he was also in financial trouble all the time. And apparently, Wikipedia says that he managed to keep himself solvent by gambling well, and he was also apparently a very strong chess player. So he had some writings about, basic things of probability theory, like binomial distributions, and what is the distribution of observing different combinations when you throw a dice. This is around 1560, but his writings were not published until like 100 years later. So first kind of known published writing on probability theory is the communication between Fermat and Pascal. So this is Pierre de Fermat and Blaise Pascal. They all had a communication of on a problem they called the problem of points. Basically, the question is the following. So suppose you have a gambling game. So again, people were always thinking about gambling. So the question they were trying to answer is that, suppose I had a gambling game. So typically gambling games end when one person goes completely broke. I mean, you win some, lose some, and keep going until you completely go broke, or the person you're playing with completely go broke. So the question they were trying to answer is, suppose the gambling game gets interrupted, then what should be the fair division of the stake? Suppose I cannot complete the game, how should I divide the stake fairly? Which basically, if you translate it in the language of modern probability, is basically asking that, my game will stop if I either reach 0 or reach 100, and I'm at 80. So if the game is interrupted, how much should I pay to the guy who will get the whole 100 amount 100 if it reaches 0, and how much should I keep? Whereas I get the whole amount if I reach 100. So this is like modern day, this is known as gambler's ruin problem. So they are sort of discussing problems like that in like early to mid 17th century. And then this person is this Poisson. He, of course, you must have seen Poisson distribution or Poisson process named after him. Bernoulli and De Moivre, Laplace, you have already seen these people. So this is actually Daniel Bernoulli. So Bernoulli family is a very interesting family. So this is Jacob Bernoulli. So they are all Swiss mathematicians. So Jacob had a brother, Johann, who's also a very famous mathematician. He did a lot of work in calculus. And Daniel is Johann's son. So Jacob Bernoulli is Daniel Bernoulli's uncle. Daniel Bernoulli did a lot of work in hydrodynamics and kinetic theory of gases, which are quite close to modern day probability. And they have many interesting stories. So Daniel's father, Jacob's brother, Johann, was apparently very jealous of his brother and his son. So he kept competing with them and kind of predated his results to say something that he had proved it earlier than his son. It's a very interesting story. You can look up if you are interested. So the Bernoulli family is a very interesting family. All of them are very accomplished mathematicians. So this is sort of the Middle Ages, like 1900 to 1950, more sort of the foundational years of probability. So Kolmogorov we have already seen. So Kolmogorov is the one who established probability theory as a discipline of mathematics. He kind of axiomatized probability theory. He sort of shows that the axioms of measure theory is kind of enough to deal with probability theory. Khinchin you have already seen. So he has law of large numbers, law of iterated logarithms, if you have seen, so lots of other work. So they are Russian people did a lot of work in probability theory in the early years. So this is Joseph Doob, who had done a lot of works on martingale. So these are basically people whose names are attached to theorems you see in textbooks that you read if you read probability theory. So this is Markov. Markov, whose name is attached to Markov chains, Markov inequalities that you might have seen. So Markov is also again is an interesting family. I mean, he also is a family of mathematicians. His brother Vladimir Markov was also a mathematician who tragically died early. So it's an interesting thing. Again, I found out recently that they have an inequality called Markov brothers inequality, which the two Markovs prove together. This is not the Markov inequality. The Markov inequality that you know in probability theory, it's something different. There is something called Markov brothers inequality, which is a bound on how fast the derivatives of polynomials can grow. So this was also proved by Andrei Markov, this Markov, and his brother Vladimir Markov. And his son was also a very accomplished mathematician, did a lot of work in recursive function theory. So this is Norbert Wiener, who developed the mathematical theory of Brownian motions. If you have seen this or heard about it, I'm sure you have heard about it. And this is Paul Levy, French mathematician who did a lot of work in Brownian motion in 1940. So these are people, again, don't go thinking that these are the only people who contributed to probability these years. I have limited space to put pictures, so there are some of the representatives of a lot of great men doing a lot of important work in probability theory. So this is more recent years, some of the modern giants of probability. So the people at the center, unfortunately they are no more. So this is Harry Keston and Oded Schramm. They have contributed a lot on many different areas of probability. So Keston is the one who proved this p equal to half is the point where this transition happens in percolation. He had done a lot of work on random walks, percolation, basically a lot of other areas. So he was one of the most versatile probabilists of 20th century. This is Oded Schramm. He had done also a lot of work on percolation, and in particular, he's famous for defining this process SLE, which is now named after him, Schramm-Lohner evolution, which is one of the most important discoveries in probability theory in the last 35 years. People at the left, you might have seen some of them. So these are 4 Fields medalists of probability. So let me start with Wendelin, who got the Fields Medal in 2006, Stas Smirnov, and Hugo Duminil-Copin. So Smirnov got Fields Medal in 2010, Hugo got in 2022. So they have all contributed, made fundamental contributions in percolation. So Wendelin has done a lot of work on SLEs also. And this is Martin Heirer, who got the Fields Medal in 2020 or 2014. He has done a lot of work on these randomly growing interfaces, that problem that I showed you about. So he has done a lot of work on something called the KPZ equation, which is related to that randomly growing interfaces. And people on the right, again, so this is Michel Talagrand. So these two people on the right, they are very famous probabilists. They had won the only 2 probabilists to win the Abel Prize. So this is Michel Talagrand. He had done fundamental work on concentration of measure and spin glasses. I don't have time to explain what these are. This is Varadhan, who has made contributions. I mean, he is a pioneer in the field of large deviations. These are probably the 2 most famous women probabilists. This is Alice Guionnet, who had done fundamental works in random matrix theory. This is Jennifer Chase. She started out as a mathematical physicist, probability theory, then moved on to theoretical computer science. She has done many works in percolation and of late networks. And she, for many years, managed research labs in Microsoft. Currently, she is the dean of the School of Data Sciences in UC Berkeley. So these are some of the, again, a very representative picture. A lot of other great people, but some of the people whose work I personally admire a lot. And last but not the least, In India, we have a quite strong heritage of probability and mathematical statistics, partly due to the early establishment of Indian Statistical Institute, but not now it has spread all over India. So some of the famous Indian probabilists. So Varadhan we have already discussed. So this is Saurabh Chatterjee. He's the most famous Indian probabilist of the current generation. He has done a lot of work on normal approximation, spin glasses, statistical physics, rigorous statistical physics, and so on. This is C.R. Rao, who was the doctoral advisor of Varadhan. So he is classified as a statistician, but many of the early works of C.R. Rao he did, they would be called probability today. So there are these famous theorems called Kramer-Rao inequality or Rao-Blackwell bound. They are quite fundamental contributions in mathematical statistics early on. So this is Parthasarathi, who's also another student of C.R. Rao. He passed away a couple of years ago, another Indian giant of probability theory. He had done a lot of work in foundational works in probability theory. His book, Probability Theory on Metric Spaces, is a classic book. Has had also done a lot of work in quantum stochastic calculus. So this is Bahadur, Raghuraj Bahadur. He was also a mathematical statistician. Again, he did many important work. This is R.C. Bose, Rajchandra Bose. So he had done a number of fundamental works in design theory. So at the intersection of statistics and computer science and combinatorics. So some of the leaders among Indians in probability and mathematical statistics. So we have a very strong heritage, and the people who are carrying on this heritage in the current generation. So it's a very strong heritage that we have. So I just wanted to tell you about these people, these giants that have contributed a lot. So I think that's probably it. Oh, okay, so I should end with this. So this is kind of a quote I like a lot. So again, so as I started with, so what we're trying to do is trying to find some patterns in randomness. So there's a quote from Hamlet. How many of you have read Hamlet or know about Hamlet? Not a lot. Yeah. So there's a quote in Hamlet with Polonius. Polonius is the advisor of Claudius, who murders Hamlet's father and becomes the king. So it says, like, it's madness, but there is a method in it. So somehow I always think about probability in that. So it's random, it's chaotic, but you actually, if you look properly, you can find structures in it. So this is a picture from an 18th century or 19th century British artist, where it's a scene from Hamlet, where Hamlet mistakenly stabs Polonius through a curtain. And it's a caution. So whenever you are making decisions based on probabilistic considerations, there are always chances of errors. You can always make mistakes, but what you need probabilists for, what you need to study probability for, is they will tell you how much is the error, how to sort of control the error, how to assess the error. So you don't need a probabilist to tell you that, okay, so I can take the average of all the observations to get an estimate of the mean of the population. But what you need a probabilist for is to assess what the error should be. When you are doing it, how much error is too much, how much error is too small. So that's where probabilists come in, and that's why they play important role. As I said, it's many branches of quantitative science, both in industry and academia. So it's a beautiful subject, and it's also extremely useful. So I end at that note. You should, this is an invitation, as I said in the title of my talk. So you should learn probability theory, and whatever you do, as long as you do anything related to science, you're going to need it. It's going to be extremely useful, and it's also very, very beautiful. So that's how I end my talk. Thank you for the attention.
Hello. Thank you so much for the enlightening talk. Please feel free to ask questions. Are there any questions? Hmm?
Oh, it's
Like
one
to
Shiva
get
had in his
this.
office. Okay. All right. So here is this the actual physical Galton board, which Shiva has kindly brought from his office. So it'll be here. You can do the experiment yourself. It's a nice thing to play around with. Right.
Okay, so if there are no more questions, then we will thank the speaker once again for the amazing talk.